Okay, in this video we will see walking through the test. To make sure our wake-word detection system is reliable, we perform extensive testing on each components. In this ensure that every part of the pipeline works correctly before putting it all together. For example, the microspeech test.cc runs inference on spectrogram data and checks that the model produced the right classification. The audio provider test.cc it verifies that microphone's input is captured correctly, while future provider mock test.cc uses a mock audio source to test future extraction with needing a real sounds. Next, recognize command.testcc confirms that the system interprets model output properly and detects the valid commands. Finally, command responder test.cc it checks that the responder is triggered correctly, such as lights and LEDs are sending a lights. Okay, next we will see the basic flow. In the wake-word detection system follows a structured workflow to process audio and detects words like yes or no. It's optimized to run efficiently on microcontrollers while staying accurate. The process begins with model setups where a pre-trained TensorFlow lights models is loaded and optimized. There the next command on comes memory allocations. Ensure input, output and intermediate data have a space to run smoothly. The system then performs spectrogram generation, tuning a raw audio input into a frequency based image representation. In this spectrogram is passed to the model for inference executions, which is assigned probabilities to each word. Finally, in a wake-word detections, the system compares scores and triggers and actions if the target word is identified. The next is audio provider. The audio provider is the first step in our wake-word detection pipeline. Its job is to capture and deliver a raw audio data from the microphones to the rest of the system. Because each hardware platform like Arduino, STM32 or Spark Fun Edge handles the audio differently. The audio provider must be customized for each device. The key features include connecting the microphone's hardware to the software, capturing a 16-bit PCM audio samples in a real time, and using the functions get audio samples to retrieve audio segments for the analysis. It also tracks timestamps to keep future extractions aligned with the latest input. By supporting multiple platforms through the custom implementation, the audio provider ensures flexibility across different hardware setups also. Okay, next we will go to the feature provider. The feature provider is the critical components that transform raw audio into a spectrogram. As a structured format the model can actually understand. A spectrogram gives a visual view of sound frequency over time, which makes speech recognition much more effective. Its the main functions include converting audio into a usable format, extracting frequency patterns with the fast Fourier transformer, and the processing overlap on seconds windows of sounds. This overlap ensures real-time detection, where the old data is removed and the new data is continuously added. To create the spectrogram, the audio is split into a 30 millisecond slice, with each slice overlapping by 10 milliseconds. Each slice undergoes FFT, producing a 256 frequency values. That's values are grouped into a 43 frequency buckets, forming a single row of the spectrogram. By stacking a 49 rows, we get a full 1 second spectrogram, which becomes the model's input for the classifications. Next, we will see the command recognizer. In the command recognizer is the part of the system that takes the raw probability scores from the model and decides whether the wake word has truly been spoken. Instead of relying on a single inferences, its average predictions across multiple time steps. This smoothing technique increases accuracy and avoid reacting to random spikes in the output. However, there are challenges in word detection. Partial word detections can occur if only part of the word is captured, leading to errors. Background noises may inference, causing a false activation in noise and environments. And repeated detection can happen when the same word is recognized multiples in a short period. The recognizer must handle this issue to deliver reliable results. In that, we will see in the figures the word as being captured in our windows. Figure 5, part of the word no being captured in our windows. The command recognizer works by talking the continuous stream of inference results from the models and analyzing them over time. Instead of acting a single prediction, it averages the scores across the multiple inferences, which makes detection more stable and accurate. In that, applies on detection threshold to ignore weak or uncertain signals to avoid repeated triggers. It also uses as suppression time, meaning once a wake word is detected, that system will wait briefly before accepting another detection. Finally, a wake word is only confirmed the constant pattern of the strong prediction is observed. This combination ensures that the recognizer is both reliable and resistant to noise. Okay, I will stop here. Next video we will see about command responder, listening for wake words, deployment to the microcontrollers and optimizing the performance.